Hello everyone, we're looking at question 9 of winter 2018, paper 42970. The question reads, a hall probe is placed near one end of a solenoid that has been wound on a soft iron core as shown in figure 9.1. The current in the solenoid is switched on. The hall probe is rotated until the reading VH on the voltmeter is maximum. Okay, and they have given us a graph. The current in the solenoid is then varied, causing the magnetic flux density, which is denoted by capital B, to change. The variation with time t of the magnetic flux density B at the hall probe is shown in figure 9.2. So as we can see that we have the magnetic flux density and then we have time here, and at time t0 the hall voltage is V0, which is the maximum. And on figure 9.3, draw a line to show the variation of the time t of the hall voltage for time 0 to time t4. Now, one thing I would suggest you to do whenever you have graphs is that you should look at its axis and then find out its gradient and see if that can give you a value or give you something tangible, because when you're looking at gradients or when you're looking at area under the graph, that can help you a great deal in understanding how to plot the graphs. For example, I can see that I have the magnetic flux density here and then I have time here. Although I do know that magnetic flux density against time does not give me anything, but what I do know for certain is that we're dealing with hall voltage here. So first thing that I would suggest you to do is that you note down the formula for the whole hall voltage, which is hall voltage is equals to I B divided by N D Q. Do not confuse this T with this T, because this T denotes time here and this T denotes thickness here. This is the formula for hall voltage. If you wish to look into the derivation of this formula, then you have to click on the link on the top right corner. That it will provide you with a very easy derivation of this formula. Okay, so now that we have this formula IB over NTQ, I can see that B against T is not giving me hall voltage. However, considering these three as constant, because we know that the number density is constant because they haven't even talked about it, so we're going to consider them constant. Thickness is remaining constant because we're using the same solenoid and we have the same Q, we have the same current as well. So we can simply say that hall voltage is directly proportional to magnetic flux density, which is capital B. Having said that, now simply you have to look at this graph. We can see whatever is happening to the magnetic flux density in this graph is going to happen to hall voltage as well. So you take your pencil and you say, oh, at time 0 it's 1, and we know at time 0 it's V0, so I'm going to put a dot here, and then it's remaining constant till time t1. So we know hall voltage is going to remain constant till time t1, so it has to be a straight line. I'm sorry for this crooked line, but it has to remain exactly the same as this. And then we can see that there's a negative gradient from t1 to t3 going down, so we're just going to copy that and bring it down as well, and simply we can see that it's constant again in the negative direction, so we're just going to put this. So it's the exact copy of this. It's just about understanding the axis and sort of creating a link between the formulas. moving on towards the B part, that says the Hall probe in A is now replaced by a small coil of wire connected to a sensitive voltmeter as shown in figure 9.4. The magnetic flux density normal to the plane of the small coil is again varied as shown in figure 9.2. On figure 9.5, draw a line to show the variation with time t of the EMF induced in the small coil for time t0 and time t4. Again, the best thing that you can do is you go back to this part, to this graph. And because the reason why we're looking at this graph is because they have mentioned figure 9.2, so we're looking at this. And I'm going to try guessing what gradient can give me and all. But before that, you have to see if you have any formula for this EMF induced. Yes, we do. The Faraday law says that the induced EMF is directly proportional to the rate of change of magnetic flux linkage, which means I can say EMF is equals to negative of delta N into BA, and then you just divide all of this by delta T. Now, delta T here is the time, delta N the number of turns, and then you have the B, and then you have the area. Now you have to cancel out things that you think are going to remain constant and then see if any relation forms. In figure 9.2, they have given a graph of B against T, the magnetic flux density against time, and we can see that we do have magnetic flux density here and time here as well. And we do know they haven't mentioned anything about changing the number of coils or changing the cross-sectional area because we're keeping the same solenoid, so we can say that these remain constant. So in simple words, we're left with E negative of B over delta T. Now, what does this negative sign mean? That means now that we have cleared that the gradient of figure 9.2, the gradient of this figure is going to give me my EMF. However, it's the negative. So whatever is happening to the gradient in figure 9.2, we're just going to sort of take the negative of that and make this graph. Let's look at this. What's happening to the gradient from 0 to T1? We can see that it's a horizontal line, and whenever you have a horizontal line, we know that the gradient is 0. So simply all you have to do is just make a 0 line. And you can see even here the gradient remains constant. The gradient is 0, not constant, the gradient is 0. When gradient is 0, so you just have to form here as well. Now we're only left with this important part. We go up back again, and we can see that the gradient is, what can we deduce from this line? First of all, it's a straight line, so I can say that the gradient is negative. Okay, I'm just gonna write negative. The gradient is negative. And number 2, the gradient is constant. Now that I have deduced these two things, I know that the negative of this gradient is going to give me EMF. So negative becomes positive. So I know one thing for certain, that it's going to be in the positive side. And constant gradient means that it's going to be a constant value. And you just have to form a line here, and that is it for your, just draw a solid line here, and you can just sort of like connecting them together with dotted lines like this. And this is it for your B part as well, and for the question number 9.